Statistical process control. If you're in a manufacturing environment, they do this because they care. And this data that they obtain can help them make the process better. They can make adjustments to their machines so they can be in control and produce a quality product. So for example, M&Ms. Approximately 24% is supposed to be blue M&Ms. That's their target. But there's some variability in the process from 24.3 to 26%. So when you do the math, that actually comes up to what's known as 3 sigma level of quality, or 99.74% have no defects. So that means that 0.26% have defects. Still, you want to reach 6 sigma, which is a 99.99 and several more nines, where you only have 3.4 defects per million. Yes, I said million with an M. Only 3.4 defects. So let's figure out. Let's go ahead and design or take a look at a quality control chart for blue M&Ms. So if we bought 6 bags of M&Ms and plotted how many of them or what percent were blue M&Ms, here's where they would plot on the line based on an upper control limit and a lower control limit. Now these control limits are developed on 3 sigma from your target. So we see that all the points except for number 6 are within our control limits. So if they're within our control limits, we really can't do anything because that's random variation. Because it's random, we can't pin down exactly what happens that causes that. But see how number 6 happened to be outside the control limits? So we should be able to identify why number 6 had a lower percentage of blue M&Ms. So if we were to take a look at that, we should be able to track that down. But when quality control does this, they're not just taking 6 samples. They might be taking 600 samples. So you can see data points, a lot more data points on a chart. That's why a visual makes it a lot easier to identify patterns. So here's 2 questions that we might want to ask. That as a consumer, you might ask, are my favorite colors inside a bag of M&Ms? Well, it turns out 30% of customers like the brown M&Ms, 20% like red, 20% like yellow, and then we have 10 for blue, orange, and green. Well, next we need to figure out, because an attribute, is the color here. But am I getting my money's worth? So we can say that a bag of M&Ms is 89 grams. It weighs 89 grams. And that each M&M weighs 0.86 grams. Well, if we do the math, 89 divided by 0.86, it comes up to roughly 101 M&Ms. So out of 101 M&Ms, we can then figure out, well, if we're trying to go for 24% blue, well, that's how many blue M&Ms should be in there. And we can do that for the rest of the color M&Ms, but I don't have the data for that. So we can create a lot of different charts with this kind of data. So the first chart we're going to talk about is what's called a mean chart, MEAN. And when I say that, it means it's an average chart, meaning average. So it's X bar. Sometimes it will be called an X bar chart. So we have our samples, sample numbers, and then the sample size. So every sample batch had 4 in this example, and then we had 10. So we had 40 samples essentially. And these are pipe measurements. So every sample had an average. So on the right-hand side, you have your sample average, which is an X bar. And then if you go all the way down, we have a grand mean. It's a double X bar, or double bar X. So that we have, that's the mean of the mean, or the average of the average. Then we have our standard deviation. So if you are doing this in Microsoft Excel, you can just put it in and have it do the standard deviation for you. Relatively easy. So we needed to, so our first step was defining that sampling plan. They wanted to do 10 samples with 4 units per sample. So we need to calculate that center line for this. So we have to calculate the mean from every sample, which was our step 2. And then we got our standard deviation on the chart here. But we need to calculate our upper and lower limits, our control limits. So we're starting to get into a little bit of math. So our upper and lower control limits, so that equals our grand mean minus our standard normal variable, which is the z, sigma, and then which is our sigma x bar. So standard deviation of the distribution of sample means. So that's going to come up with our upper and lower control limits. So based on the chart there that we had in our first one, our upper and lower control limits are 1.375 for our upper and 1.225 for our lower. So that was our third step, coming up with this. Our fourth step is making these results visible on a chart. So it's just a simple line graph, line chart. Now we had to throw in the upper and lower control limits. So those are also lines, they just don't go up and down. So we have to plot the data with that in there. As you can see here, nothing exceeded our control limits. So for my purposes, I would say that this process is in control because nothing is going outside the control limits. And it's as simple as that. So what about creating an alternative chart for our mean here? So we have some other values that we can factor in here. We have our A2, our D3, and D4. So we are working with ranges also. So on our chart, we have the information we had from before, our sample average, but we added another column called range. And at the bottom, we also have our mean range or average range. So when we look at this, we're going to be using the sample size. So we have 10, but we have 4 samples in each one. So we're going to actually be using the 4 because we have 4 samples, 4 actual units per sample. So A2 is going to be 0.73 and our D4 is going to be 2.28. So 1 and 2 are the same, but step 3, we're going to use a slightly different formula. Our upper and lower control limits, so we have our grand mean, that's the X double bar here, plus our A2 value, which was 0.73, multiplied by our range mean, which was 0.1. So if we go down to the bottom, our upper control limits are 1.373, and our lower control limits are 1.227. These values are very close. They're just a little tighter than a standard range or standard mean chart. We're using range. So this actually made it a little tighter. So we can create a range chart using the same data. We're just using the D4 and D3 values. So remember, our D4 value was 2.28. So if we look at it, our upper control limit is going to be 0.228, and our lower is going to be 0. Remember, this is a range. We can't have a negative range. It can't happen. So our lower control limit is usually, if not always, going to be 0. So we just need to plot the chart. So this is what our chart's going to look like, our range chart, or R chart. So our center line is 0.1, and everything's dancing around 0.1. I would say it's in control. So how do you determine if it's in control or out of control? Well, we have these 5 rules. Now there's more rules, but these are the major ones. So the big one right here that I was looking at, a single point plots outside the control limits. In the last couple control charts we looked at, there were no data points outside the control limits. So we were in control according to that one. 2 out of 3 successive points are on the same side of the center line and farther than 2 sigma from it. Now we need to figure out what 2 sigma is to know this one. Most companies have software that automatically generate these charts, and they will tell you if it's in control or out of control because they've been programmed with these rules. So knowing these rules is helpful, but just to be honest with you, there's software for this. But that doesn't mean you shouldn't be aware of them, because you might have to figure out why, and seeing these can lead you to look at certain machines maybe on the production line rather than certain areas. So 4 out of 5 successive points are on the same side of the center line and farther than 1 sigma from it. A run of 8 in a row that are on the same side of the center line. Any consistent or persistent pattern that tells you your process includes systemic variation. So you might be able to see a pattern with more data points. Now, our charts only had 10 sample groups of 4 each, and I didn't see a pattern. But if you have thousands of data points, you might be able to see a pattern. So these statistical charts that we've created or we've gone over help us determine if our process is in control. They are not the only tool in the toolbox. And sometimes we know there's variation, but we accept it. Or we work so hard to try to eliminate it, but we just can't. So sometimes we just have to go with it. But there's also something called random variation that we can do everything we can. It just doesn't work. We can't fix it. So you need to understand what you're looking at and how to analyze it. So next we're going to move on to cause and effect analysis. And with that, let's move on.